Hello everyone from Math 1340, Statistics. It's Professor Wenson here again with a video on your KnewtonAlta homework for section 5.1 titled Continuous Probability Functions. So we saw in chapter 4 discrete probability distributions, right? Discrete probability functions. And remember, a discrete random variable was where the possible outcomes, could be counted. Numbers of cars, numbers of books, whatever. Numbers of successes with a binomial probability function. In this chapter, right now we're only doing the one section from chapter 5, section 5.1. Remember, continuous variables are ones where the possible outcomes are measured, not counted. They have to be measured in some special way. So, like heights, weights, times, temperatures, things like that. All right. So here I am in the preview. Again, you're not going to see the word preview for the section 5.1 KnewtonAlta homework. There is only the one objective this time. So hopefully this is a shorter assignment. And it's use area under the curve to compute probability for continuous probability density functions. So the first time I'm seeing this objective, I'm going to go to more instruction here and view instruction. Okay. So area under the curve to compute probability for continuous probability density functions. All right. Continuous random variables have many applications. Baseball batting averages, IQ scores, the length of time a long-distance telephone call lasts, the amount of money a person carries, the length of time a computer chip lasts, and SAT scores are just a few. The field of reliability depends on a variety of continuous random variables. So a note here about the difference between discrete and continuous yet again. So the values of discrete and continuous random variables can be ambiguous, hard to determine, hard to tell the difference between. How the random variable is defined is very important. For example, if capital X is equal to the number of miles to the nearest mile that you drive to work, then X is a discrete random variable because you're simply counting the number of miles, right? I've driven 1 mile, 2 miles, 3 miles, 4 miles. Something counted is for a discrete random variable. But if X is just the distance you drive to work, then you measure the values of X, and in that case X would be a continuous random variable. Because the distance you drive to work could be 3.48 miles, 3.579 miles, 5.22296 miles, whatever. There's a measure to it that you would need some special instrument to determine. Right? Whereas the numbers of miles to the nearest mile could be counted. For a second example, if X was the number of books in a backpack, right, then X is a discrete random variable. Like this person has 2 books, 5 books. It's something that can be counted. 1, 2, 3, 4, no books, But if X was the weight of a book, then X is continuous, because weights are measured, right? Again, good rule is if you need a special instrument to determine your values, it's more than likely a continuous random variable, something that needs to be measured. Like you would need a scale to measure the weights of these books. All right, so some properties of continuous probability distributions. The graph of a continuous probability distribution is a curve. All right, if you remember from chapter 4, the graph of a discrete probability distribution was just a histogram, right? Just I used a few rectangles, right? Connected rectangles, or from section 4.3's KnewtonAlta homework, they had some graphs there where they weren't rectangles, but little sticks, with certain heights. But you could also replace those sticks with bars and make a histogram. All right, so discrete probability distributions, when you look at a graph of those, is a histogram. Continuous probability distributions are curves. All right, so no bars. They're just like curves in graphs in algebra. Probability is represented by area under the curve. That's a huge thing here. That's what this whole objective is about. All right, the curve is called the probability density function, PDF. Just like for discrete, right? You had discrete probability density functions or probability distribution functions, PDFs, but this time we're looking at, again, a curve and not a histogram. We use the symbol f of x, right? Just like a function in algebra, right? F of x, to represent the curve. F of x is the function that corresponds to the graph. We use the density function f of x to draw the graph of the probability distribution. We define a function, f of x, so that the area between it and the x-axis is equal to the probability. Again, area under a curve and probability are hand in hand. So in the study of probability, the functions we study are special. Since the maximum probability is 1, the maximum area, right, under the entire curve that's drawn is also 1. So they put this in bold here, a huge thing. I've mentioned it already. So for continuous probability distributions, probability equals area. Now you've already come across one part of this text of the KnewtonAlta homework where this is covered. You've already come across this concept. If you recall the empirical rule for normal distributions, remember bell-shaped curves? Those were continuous density curves. Those symmetrical bell-shaped curves. And you recall that the area under that curve, under a symmetrical bell-shaped normal curve, the area under the curve that's within 1 standard deviation of the mean was approximately 68% of the entire area. The area under the curve within 2 standard deviations of the mean was approximately 95% of the entire area. And the area under the curve, right, again a normal symmetrical bell-shaped curve, the area under the curve within 3 standard deviations of the mean was approximately 99.7% of the entire area. And then the entire area under the curve from the far left to the far right, the whole thing was 100%. So you've seen this concept brought up before in that empirical rule for normal distributions, normal bell curves. But now it's going to apply to other curves as well, other continuous probability density functions. All right, so the area under the curve looks at an interval of values, right? Not just a single value, instead of just an individual value to evaluate probability as area. All right, so some key points. As they said earlier, the outcomes are measured, not counted, right? It's continuous random variables, not discrete. The entire area under the curve above the x-axis is equal to 1, right? So the area under the entire curve is 100%, 1. Right? That's basically the same as for discrete variables, where you said remember how if you add up all the probabilities, you get 1. That's the same kind of concept here. Probability is found for intervals of x values, like they set up here, rather than for individual x values. Right. which I'll talk more about down here. Here, the probability that x is between c and d, right, is the probability that the random variable x is in between the values c and d. So, this probability that x is between c and d is the area under the curve above the x-axis to the right of c and left of d, right? So that you're between c and d on the x-axis. The probability that x is between c and d without c and d is the same as if you include c and d, because probability is equal to area, right? Adding two individual values, adding c and d to the interval, doesn't affect the area, as we'll see later. And the probability that x equals an individual value equals just c, that probability is equal to 0. Because if we're corresponding probability to area, if I mark off just the value c and find the area under the curve at just one value, that's just a segment. And a segment has no area, 0 area. All right. So the probability that x takes on any single individual value is 0. Right, the area below the curve above the x-axis, and between x equals c and x equals c is no width, right? Again, it's just a segment, therefore no area. We will find the area that represents probability by using geometry, formulas, technology, or probability tables. When we use formulas to find the area, the formulas were found by using integral calculus. Don't worry about that. You're not going to have to be using calculus here, I promise you. There are many continuous probability distributions, right? Just like there are many different kinds of discrete probability distributions, right? We had the binomial, geometric, hypergeometric, Poisson, all those were mentioned in chapter 4. You only studied the binomial though. And here, there are many different kinds of continuous probability distribution as well, and thus many different shapes underneath the curve of the distribution. The following graphs illustrate some of the distributions we will study. Now, we're only doing the normal. We'll also come across one in a later chapter called the student's t distribution. We'll also come across another distribution called the chi-squared distribution. That's another continuous. So normal, student's t, and chi-squared are really the only continuous distributions we're going to be studying in detail in this course. But they do mention some other types here. There's something called the uniform distribution, which the curve is just a horizontal line. And then there's the exponential distribution, which again, the curve is like an exponential function. Remember, like algebra class, what an exponential function looked like? This is a decreasing exponential function. And again, the one we're going to study more than anything, the normal distribution. Remember, the normal distribution is a symmetrical bell-shaped curve. Okay, we're going to be studying that more often than anything else. But again, they mention here, look at shaded area. Area under curves will represent probabilities of your random variable taking a value in certain intervals. All right, so they go over this first example here. I'm just going to get to a question. You can read these examples on your own. I'll just get to a question. So it says, now this is one of those uniform distributions, right? The curve is a horizontal line. It says, given the graph below of the probability density function f of x, what is the probability that the random variable x takes on a value between 5 and 7? All right, so I'm going to draw this and get back to you on a piece of paper. All right, so here I am. I've drawn that same picture. The horizontal axis is a number line. It'll represent possible values of our random variable x here, the continuous random variable x. And we have our curve, right, which is a function f of x. And notice that the entire area under the curve is 1, right? This is just one big rectangle. See, the width is 8 units long, right? 1 to 9, that's 8 units. And the height, see here on the vertical axis, is 1/8. And 8, it is a rectangle, and the area of a rectangle is just length times width, right? 8 times 1/8 equals 1. That's the entire area, right? Entire area under the curve. And it should be 1, right? You should double check that stuff if you can. Make sure it's actually, and this is a proper probability density function, continuous density function. Right? The entire area should be 1. And another thing they didn't mention is that the curve should be always above the x-axis. So the entire area under the curve is equal to 1, and the entire curve is above the x-axis, right? Because remember, this is just like for discrete. If any part of this curve went under the x-axis, that would imply that there was negative probability, and you can't have negative probability. Right? So a proper probability density function for a continuous random variable should have these things happening. The entire area under the curve is 1, and the entire curve is also on or above the x-axis, the horizontal axis, but nothing below. Now we are asked to find, what's the probability that if I were to pick a value of x at random, that it's going to be between, the value of x will be between 5 and 7. What's this probability? Now again, notice we're not asking for a specific value, right? Remember, if I want a specific value, if I said, let's pick a value from 1 to 9 here at random, and say, hey, what's the probability that x equals 3? You're not going to see this, right? Because if I say, what's the probability that x equals 3, a specific value, here's 3 on the horizontal axis, this is the area that's being talked about there. And you see, that's just a segment. And a segment has no area. So this was mentioned earlier. Remember, for a continuous random variable, the probability of that variable being equal to a specific value will always be 0. All right, but we're not asked that here. We're asked, what's the probability that the value you choose, right? Again, we're going from, this curve is only above values 1 to 9. So if I were to choose a value from 1 to 9 at random, what's the probability that that value will fall between 5 and 7? So from here to here, right? From 5 to 7. So then I find there's the interval that's being talked about. And then we want the area under the curve over that interval. Right? So this area right here that I've just kind of shaded. Right? So this probability is equal to, again, this area, right, the area that I've just highlighted. Now, look at this shape. This is a rectangle. And the area of a rectangle is very easy to find, right? It's just the width, which is 2, multiplied by the height. Now the height is, 1/8. Right? The height of this curve is 1/8 of a unit over there on the vertical axis. And 2 times 1/8 is 1/4, right? 2/8 or 0.25 if you write it as a decimal, or 25%. But yeah, so remember, and it's probability, right? Probability should always be some number from 0 to 1, right? Never negative, never greater than 1. And that's what's happening here. So if I were to pick a value at random from 1 to 9, with a value from this continuous variable with this density curve, the probability that that value falls between 5 and 7 is 25%. I have a 1 in 4 chance of that happening. Okay. So here, just 1/4. Right, 1/4. I mean, probability equals area when it comes to these continuous density functions. Right. They show basically the same picture I drew. Okay. And I think that's all these problems really are. Right, so again, I'm going to draw this. I'm going to draw this same picture on a piece of paper and get back to you. All right. So I've drawn this out. Now you have this continuous probability density function, this probability density curve called f of x here. I've drawn it in pink. Starts off at here at the point, 0 on the horizontal, 1/2 on the vertical. Starts off at that point, and is just this straight line, this straight segment down to this point, and then it stops, right? It doesn't go on below it, and it doesn't keep going that way. So the total area is just this big triangle here. So again, we got this probability density function. And what's the entire area under that curve? Again, it should be 1, and I'm just double checking. Now it's a triangle this time, right? The last picture was a rectangle. Now a triangle, remember a triangle, the area is half a rectangle, half the base times the height. So it'll be half times the base here is a length of 4, and the height of it is a half, right, from the bottom to the top here. So half of 4 times a half, well, that's just 2 times a half. That is 1. So good on that, right? The entire area under the curve should be 1. And again, the entire curve is on or above the horizontal axis. Because again, if any part of the curve goes below the x-axis, that would imply that there is going to be some sort of negative probability. And remember, probability can only be from 0 to 1. All right. So again, horizontal axis, possible values of this random variable called x, continuous random variable x. And looks like the only values that this could take on are from 0 to 4. All right, that's the only part. That's the only interval that this curve is over, from 0 to 4. So the question is, right, what we're asked to find is the following. Right? We're asked to find the probability that if I were to pick a value, from 0 to 4, if I were to pick a value at random for this particular continuous probability density function, this continuous random variable, if I were to pick a value from 0 to 4 at random, what would be the probability that that value falls between 1 and 4? So again, I'll highlight this. Now this is the interval from 1 to 4. That's this interval right here. And we're doing area under the curve over that interval. So that'd be this, from 1 to 4, that'd be this triangle right here, this shaded area. And probability for a continuous random variable is equal to area. Now, this is a triangle. And I just mentioned up here that the area of a triangle is half that of a rectangle, right? So half the base times the height. So half. Now the length of this base of this like purple triangle here under the curve, it's from 1 to 4, so that's 3 units, multiplied by the height. Now they gave us in the picture, they told us the height here at 1 was 3/8. So half of 3 times 3/8, which if you multiply all the numerators would be 9, right? 1 times 3 times 3. Multiply all the denominators, 2 times 1 times 8 is 16. 9/16. 9/16 would be the probability of picking a value at random from 0 to 4 and having that value fall between 1 and 4. And 9/16 is over 50%. If you want to put it in a calculator or something, get a percentage. But they're asking for a fraction here. Look at our choices, 9/16 right there. Great. And again, they're drawing pretty much the same picture I drew. All right. Now this last part, I'm going to talk about complex areas. Remember, I already talked about, we saw the area of a rectangle, base times height, length times width. We saw the area of a triangle, right? Half base times height, right? Or half length times width. So you're going to see. We're going to read this. Now, what we have here is a trapezoid. Remember, a trapezoid has two parallel sides called bases, and the area of a trapezoid is half the sum of the bases, the average of the bases times the height, right, which is the distance between the bases. Now you could think of this shape as a trapezoid, or you could break it up, break it into two pieces, into a rectangle and a triangle, and then take the area of the rectangle, the area of the triangle, and then add them up. So that's what they mean by complex areas. Right? Something you have to break up into rectangles and triangles, maybe. Ooh, real tough. Notice the sarcasm in my voice. I think this should be pretty simple. So let's take a look at an example. All right, so here the figure below shows the probability density function for the some random variable x, some continuous variable x. The shaded area represents the probability that x is between 4 and 5, right, in the interval from 4 to 5. What is this probability? And round your answer to 3 decimal places if necessary. Right. Okay, so I'll draw that picture and show you a couple ways to look at that shaded region. Okay, so here's a rough hand drawing of what they had. So you got this curve that starts here at 1 point and then 0.3 for the height, ends here at 6 and 0.1 for the height. And the horizontal axis again represents possible values of x. It looks like the values of x only range from 1 to 6, right? That's what the curve is over. And we're asked for, what's the probability that if I choose a value at random, that value is between 4 and 5. Now notice this time they're including 4 and 5, but it's the same as earlier as between 4 and 5, because including individual values doesn't change the area. Including the endpoints won't change this area. All right, so again, this is equal probability for a continuous random variable is equal to area. Now, like I said a second ago, this is a complex area where we can break it up. We can break it up into a rectangle. See this rectangle here that I'm shading in like orange. All right, we gotta do rectangle in orange. I'll put RECT. And above that, the other part of the area I haven't shaded is a triangle. All right. I'll shade this in like gray. And I'll put tri for triangle. So you have a rectangle shape and a triangle shape that make this up. So to find the total area here from 4 to 5, above the interval from 4 to 5, I'm going to take the area of this rectangle, right, the rectangle area, and then add to it the gray triangle area. Alright, so the rectangle area, in a rectangle, the area is just the length times the width times the height. So the width is 1, right? You're going from 4 to 5 here. The height is here, it's given as 0.14. Right, so there's the area of the rectangle. We'll multiply, that's just 0.14, right? Anything times 1 is itself. And then the area of this triangle, this gray triangle up here. Remember, the area of a triangle is half the base times the height. So I have a half there, or 0.5 if you want to write it. Again, the base here, the length across on the bottom here is 1 unit. I'm going from 4 to 5. Right, this here. So half of 1, which is just a half, times the height. Now the height is this distance here, from 0.14 to 0.18. That distance is 0.04. Right? 14 hundredths to 18 hundredths is 4 hundredths of 0.04. All right, now I have the area of the rectangle, the area of the triangle. Let's figure them out. So 1 times 0.14, the area of the rectangle is just 0.14 square units, plus then half of 0.04 is 0.02. So that's 2.02 square units, and then putting them both together gives me an area of 0.16. All right, so the probability, 16%. The probability, if I pick a value at random, a value for x at random, the probability that that value would fall between 4 and 5 is 16%. Right. Now, you could have also just thought about this whole shape as a trapezoid. So you could have also said that this is just the area of the trapezoid, because you got two parallel sides, right? That's a trapezoid. A four-sided figure where there's one pair of parallel sides is a trapezoid. And the area of a trapezoid is half the sum of the parallel side lengths, right? So these parallel sides have a length. This one has a length of 0.14 plus, and then the other side length that's parallel to it, this other base, has a length of 0.18. And then times the distance between those parallel sides, which is just 1 unit, right? The distance between the two parallel sides here is from 4 to 5, that's 1 unit. And what's 0.14 plus 0.18? This is 0.32. And what's half of 0.32 is 0.16 times 1 would be 0.16. So I mean the same thing, right? Because a rectangle and a triangle put together with the same distance between their parallel sides, a rectangle and a triangle put together, or a rectangle with triangles put together, make a trapezoid. So however you want to look at it, break it up into a rectangle and a triangle, or look at it as a trapezoid. If you remember how to find the area of a trapezoid, you can do that too. But either way, the area under the curve, the probability they're asking for is 0.16. Now they did say go to 3 decimal places, so I'm going to throw 0 on there. 0.160. Great work, right? Hooray. Okay. And it looks like we probably have one more here. All right, now look at this. Density functions given. Now it's not just a straight line, right? It's like a straight line and then another one, right? A little branch off, a little shot down. But again, the entire area under this blue curve should be 1 unit, and 1 square unit, 100%. And again, I'll draw this, and we're asked to find the probability, now this time not between two numbers, but just less than 2. The probability that the value of the random variable x is less than 2. So again, I've drawn that crudely by hand. So here's your density curve, right? Density function. And again, the horizontal axis represents possible values of this continuous variable x. And it's starting here, not going that way forever. And it's just starting there and ending here, and not going down. Right? Again, the area under the entire curve should be 1. You can double check that. And the entire curve is at or above the x-axis. So it's a valid continuous probability density function. We're asked to find the probability that again, if I pick a value at random, what's the probability that that value of x is less than 2? So that would be talking about this interval right here. So from 2, technically onward, but there's no graph over here. Technically there's nothing over here, so the probability would be 0. So there's no need to keep drawing to the left. So if that's from 2 to the left, so basically from 2 to 0. Less than 2 basically just means from 2 to 0 on this picture. So we're talking this area right here. And technically the rest of this, which is nothing, right? This has, all this over here has area 0, right? Area equal to 0 over here. So just this rectangle, right? Just this rectangle. Now it is a rectangle, right? So that makes it easy. Area is the width here, 0 to 2 is 2 units. The height is 1/9, right? That's at 1/9 up there. So 2 times 1/9, 2/9. Beautiful. And that's it. Again, just area under curve for a continuous random variable is probability. 2 nths. All right, I believe, like as you probably you've seen it, that seems to be every single kind of problem in this assignment. Given the graph of some density function for a continuous random variable, can you find the probability of picking a value at random and having it fall in some interval? And that will correspond to the area under the curve to the x-axis. Great. So hopefully that's not too bad. Just remember how to find the area of a rectangle, right, and the area of a triangle, or the area of a trapezoid, or that would help too. And hopefully working through, watching this video, you can use it as a guide for you when you work on the Section 5.1 assignment on your own. Of course, if you have any questions, let me know, and thank you very much for watching.